Hello, I'm coming to you today, class, with section 5.4. We're going to look at the fundamental theorem of calculus. There are a couple of other topics in this section, but that will be our main focus, and we'll get started. So let me share my screen. Oh, let me say this. This section, 5.4, what we're going to do in this section will actually make what you do in 5.3 easier. I know that sounds weird because 5.3 comes first, but 5.3 had us evaluating definite integrals using the limit definition. You don't actually have to do that to evaluate definite integrals now as we get into 5.4, the fundamental theorem of calculus. So if you did not get finished with 5.3, you can actually go back and complete those problems with the techniques that we're using in 5.4. Okay. The computer, the homework is not going to know whether or not you use the limit definition to get the final answer or the fundamental theorem of calculus. So let me start with sharing my screen. So 5.4, we're going to be focused on the fundamental theorem of calculus. Let's get into that. So the fundamental theorem of calculus, you have now been introduced to the two major branches of calculus, differential calculus and integral calculus. And at this point, the two problems might seem unrelated, but they're actually very close. And I think they actually shouldn't feel completely unrelated because we looked at limits for both. So you could kind of see the connection. The connection was discovered independently by Isaac Newton and then also by Gottfried Leibniz, who actually developed the fundamental theorem of calculus. So informally, the theorem states that the differentiation and definite integration are inverse operations in the same sense that division and multiplication are inverse operations. So they looked at the relationship by looking at a couple of topics here. Differentiation, looking at the slope for a secant line, the change in the y over the change in the x between those 2 points, and then the slope for the tangent line used as an approximation for the slope of that secant line. Remember, tangent is instantaneous slope because we're looking for the slope of the curve at a particular single point, okay? Then, if you think about it, the area of a rectangle, we found that to be the change, like for example here, the change in the y, or basically the height times the base, or the base times the height, delta y times delta x. And then we use the area of rectangles to approximate the area of regions under curves. So differentiation and definite integration have an inverse relationship. So anti-differentiation and definite integration. Let's link those now. So throughout this chapter, you've been using the integral sign to denote an antiderivative or a family of functions and a definite integral, a number. So anti-differentiation, we use this symbol and we were trying to find the antiderivative of some function f with respect to x. And then here, the definite integration or definite integral of this function from a to b, f of x with respect to x. Notice that it's the same symbol. The use of the same symbol for both operations make it appear that they are related. In the early work with calculus, however, it was not known that the two operations were related. The symbol, the elongated s, was first applied to the definite integral by Leibniz and was derived from the letter s. Okay? So the fundamental theorem of calculus basically says this. If f is a function and it is continuous on the closed interval ab, and capital F is an antiderivative of f on the interval ab, then the integral from a to b of f of x with respect to x is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. So basically what we're saying is you find the antiderivative of this function and you evaluate it at the endpoint, evaluating it at the top endpoint, and then subtracting from it that function evaluated at the lower endpoint. So the integral, the definite integral, is equal to the antiderivative evaluated at those endpoints. So we're going to be basically finding the antiderivative and then evaluating it at those endpoints. What we could have done actually in 5.3 instead of that limit definition. Okay? So you can always go back and actually look at those problems and see how much shorter your work will be now just finding the actual antiderivative. Remember, we looked at finding some basic antiderivatives by looking at that power rule for anti-differentiation. And then we'll look at a few more rules in 5.5 too. All right. So here's an example. It says, provided you can, well, some guidelines and an example within the guidelines. It says, provided you can find an antiderivative of f, you now have a way to evaluate a definite integral without having to use the limit of a sum. So it completely takes that long work out, okay? So, because I'm afraid my video may have gotten cut off at the end of 5.3. But if you have questions on that homework, I can answer those in class. But just go back and look at it and apply what we're going to be doing in 5.4 to 5.3. Also, you can take away the need of using the limit of a sum. So here you have some function f of x, and it's called x cubed. Okay, and evaluated, we're looking for the integral of x cubed with respect to x from 1 to 3. So the power rule for anti-differentiation states that we add 1 to the exponent and place that over n plus 1. Place that over the new exponent. So the antiderivative for x cubed will be x to the 4th over 4. And we will evaluate that from 1 to 3. So plugging in the endpoints 3 and then minus that endpoint 1 to get your answer. And once you are evaluating it, a definite integral, there's no need for you to put the constant C of integration when you have a definite integral. Okay? All right. One more thing in your notes, you also have the mean value theorem for integrals. I would have to look at the homework to be sure, but I'm not certain that there are any homework problems related to it, but I wanted to mention it anyway. The mean value theorem is just the area of a region under a curve is greater than the area of an inscribed rectangle, but less than the area of a circumscribed rectangle. So basically, that area under the curve, you can approximate it using an inscribed rectangle and a circumscribed rectangle, because it'll be greater than the inscribed rectangles, but less than the area of the circumscribed rectangle. The mean value theorem for integrals states that the integral, the answer would be somewhere between the inscribed and circumscribed rectangle. So it gives you an approximation of where your answer, where your area would actually fall for a particular region. Okay? And then you got the formula here for it. So the integral of the function f of x with respect to x from a to b, according to the mean value theorem, it just says is equal to the function at c, the function evaluated at some number c, some value c within the integral, and that's typically where the function equals 0, and then times b minus a, the endpoints, the difference of the endpoints. Okay? So we're going to look right at some examples. We're going to go straight into looking at some examples and go from there. All right. 5.4. Okay. And I want to say there are 22 questions in this section. All right. So the first problem just says evaluate the definite integral, use a graphing utility to verify your results. Okay, so we're going to use the fundamental theorem of calculus, right? So the integral from -1 to 0 of 4x minus 1 with respect to x. All right, so when we integrate each term, you technically could show each term with its own integration symbol, but that's not necessarily required. But you will apply the power rule, okay? So 4x becomes 4x1 plus 1 over 1 plus 1. Because that exponent was understood to be a 1, you just add 1 to that. I want you to recall what we learned in 5.1, okay? Those rules for finding the antiderivative, the power rule, to be specific, is the one I'm focused on. So then that becomes 1 plus 1 on the bottom, and I will clean that up. And then minus, you've got just a constant 1. When you integrate that, that becomes x. And again, because it's just a constant right now, the integral of a constant becomes the variable. And again, those are those few rules that we saw in 5.1. And then we will evaluate that from -1 to 0. So 4x squared over 2 minus x from -1 to 0. This becomes 2x squared minus x from -1 to 0. So 2 times 2 times 0. You start at the top one. 2 times 0 squared minus 0. And then minus 2 times -1 squared minus the -1. I'm just placing my interval values, -1 and 0, into the function. Placing the top one, which is b, and subtracting that function evaluated at a. So top one is b, bottom one is a. So this is just 0 right here. And then I got minus, let's see what this is. This is 2 times 1 plus 1, because this becomes plus. And then we square -1, that's just a positive 1. So this is 2 plus 1, which is a -3. Okay, a -3. Let's see what else we have. You can see how we just found the antiderivative of each term and then evaluated it. Pretty standard, pretty straightforward. Let's look at number 3 here. It says evaluate the definite integral from 1 to 4 of 3 over x squared minus 1 dx. Okay? So the first thing I'm going to do is bring this x squared to the top, make that a negative x squared. Okay? Now I'm ready to actually integrate. So 3x to the -2 plus 1 over -2 plus 1, and then minus 1x. Because integrating a constant becomes that constant times a variable, the variable x. With respect to dx, so it becomes x. And we are evaluating that 1 to 4. Now we'll clean that up. So this becomes 3x to the -1 over -1 minus x 1 to 4. So this is a -3 x to the -1 minus x. But that divided by -1, just bring it out front. And technically, that x should go to the bottom as well to make it positive. But since you're fixing to, well, I'll go ahead and do that. Let's go ahead and do that. -3 over x minus x from 1 to 4. So we got -3 over 4 minus 4 minus negative 3 over 1 minus 1. Evaluating both, or evaluating this antiderivative at both endpoints. So let's see what we've got. So right here, negative 3/4, and then minus 4. And then minus, I tell you what, let's put that all in the calculator. We should be able to. Let's do parentheses, negative 3/4 minus 4, and then minus parentheses, negative 3 minus 1. We got a negative 3/4 for our answer. I just put it in right as I saw it, all in. And sometimes I do that, sometimes I do parts, but that one wasn't that complicated, so the calculator could handle that. All right, let's see what else we've got here. If it's looking like these are just like repeat of the same questions over and over, I might cut it down some. I'm trying to see here. Let's see. Okay, here's a good one. And they can switch up the variables sometimes, but understand that that's not going to affect the answer. You're still going to work it the same. All right, let's take a look at, number 5. It's using a different variable. That's really the only thing I want to look at here. Let's take a look at it. So we've got an integral from 1 to 4. And then after this one, I actually want to look at one that has an absolute value in it. I think number 9 is the one I want to look at next. Yeah. Look at that. All right. So we've got from 1 to 4, number 5, from 1 to 4, u minus 5 over square root of u with respect to u, or du. Okay? Okay, now let's see what we've got. We have u and 5 both divided by the square root of u. So what I'm going to, and it's on the bottom there. So what I'm going to do is basically kind of bring that to the top, and I'm going to be multiplying both of those with it. So let's start with this. So u minus 5 over u to the 1/2 power du. And then I'm going to take that u to the 1/2 power to the top and making a negative 1/2 power. And then I got times u minus 5 du. Okay. Now we've got the integral of u to the 1/2 power. So I'm going to distribute this. So this is understood to be u to the 1. And so when you're adding, because when you multiply, you end up adding the exponents. That becomes u to the positive 1/2, because it's a negative 1/2 plus 1. And then minus 5 u to the negative 1/2. And then du. Now we're actually ready to integrate, because we actually haven't integrated yet. But now we're ready to integrate. So we've got u to the 1/2, so u to the 1/2 plus 1 over 1/2 plus 1. And then minus 5 u to the negative 1/2 plus 1 over negative 1/2 plus 1. 5 is just a constant multiple, so it kind of just hangs out. And this gets evaluated from 1 to 4. We're going to clean it up. So u to the 1/2 plus 1 becomes u to the 3/2. And then that's over 3/2. So instead of writing this over 3/2, we're going to put times 2/3. Okay, looks better than having 3/2 in the bottom here. We flipped it and multiplied it, made it 2/3. Right here, that 5, and this is over a half here because the negative 1/2 plus 1 becomes a positive 1/2. Well, you're going to flip that and multiply, so it's going to be times 2, and you get multiplied with that 5 right there. That's going to come down to minus 10, u to be positive 1/2, because the negative 1/2 plus 1 is a positive 1/2. And we're going to evaluate that from 1 to 4. Okay? So from 1 to 4, so you got 2/3 to the 3/2 power, and then minus 10 to the 4 1/2 power, then minus that whole thing again at 1. So I might want to do brackets or braces around that, and then show that now I'm going to put that same expression down where this time where I've got u, I've got 1. I'm going to replace it with 1. Okay, so let's clean this up. Okay, all right. So 2/3 times 4 to the 3/2 power. So 2/3 times 4 raised to the 3/2 power. All right, then minus, and this is technically just 2. 4 to the 1/2 power is the same thing as the square root of 4. That's just 2. So this is minus 10 times 2. So let's just say 20. Let's just say 20 right there, minus 20. All right, ooh, let's give me some ugly number. Let's see what we got. So this right here is a negative 44/3. What we got there. Then I'm going to subtract from that this. Let's see what we get here. Well, anything to the 1 power, or 1 raised to any power is still just 1. And then minus 10. So here we get a negative 28/3. So it's minus, but then it's negative in here as well. That's technically going to become plus. So negative 44/3 plus 28/3 gives us negative 16/3. That's our answer. That is our answer. Okay. Let me see what else I've got here. That was number 5. Oh, let's look at number 9. It's dealing with an absolute value one, and technically, when you're dealing with an absolute value one, where you've got, let me show you here, number 9, the integral from 0 to 3 of 2x minus 3 dx. Oh, I'm sorry. Okay. So the issue with this, anytime dealing with absolute value, and there may be one in the homework. Well, no, this is the homework. I'm sorry. There may be one in the textbook, an example also like this that you can look at and get more details. But I'm going to try my best to explain why I'm doing what I'm doing. When you're dealing with absolute value functions, show you something. Look at the graph here. I want you to see something. For absolute value, we're going to press math. We're going to go over here. There it is right there under EM. Absolute value with the parentheses, ABS, that represents absolute value. So it brought in, so we brought in the absolute value symbols in y equals. I'm going to type in 2x minus 3, hit graph, and it's going to give us a v, okay, as you can see here. So the issue is that we want to evaluate this function, or the integral, from 0 to 3, but what's happening here is the function gets chopped. It's got half over here, half of the area under the graph is here between the y-axis and this intersection point, or this x-intercept where it crosses or touches the x-axis, which is the 0 of the function. And then over here to 3, we cut it off right here where x is 3. We've got another little area under the graph. So it's like you've got these little regions that you want to find the area of. So what we're going to do is we're going to break these two, we're going to break this whole integral. We're going to break this whole integral over into two parts where we've got this area here from the y-axis, which is at x equals 0, to where it touches the x-axis, and then from where it touches the x-axis to 3. So because the region is kind of broken, the region under the curve is kind of chopped by it being an absolute value function, we're going to split it into two integrals. So because the region under the graph is separated by the x-intercept, where it sits on the x-axis, we're going to divide the integral into a sum of 2 integrals. Okay? So we need to figure out, I get that off, we need to figure out, where that x-intercept, where that 0 of the function is. Okay? So we're going to hit second calc to figure out where that 0 is, where it actually intersects the x-axis. And we call that a 0. It's a solution. All right, so left bound, I am to the left side of it. I can get a little closer if I want to, but I'm to the left side of where that intercept is. And then I want to be over here to the right side of it as well. And then I'll press enter. And that 0 is at 1.5, so 3 halves. So you can do 1.5 or you can do 3 halves, either one. So the graph of 2x minus 3 has an x-intercept, which is just a 0, x-intercept, just a 0 of the function at x equals 1.5, which is 3 halves. Okay, so what I'm going to do is split that integral up into 2. So from 0 to 1.5, 2x minus 3, respect to x, plus 1.5 to 3, of 2x minus 3 with respect to x. Okay, that's how we have to approach this problem. Beyond that, it's pretty standard integration, finding the antiderivative. So the antiderivative of 2x is 2x squared over 2, which will actually just be x squared. The integral, or the antiderivative of 3 becomes 3x. So that will be evaluated from 0 to 1.5. And then, same thing, 2x raised to the 1 plus 1 exponent, bottom 1 plus 1, and then minus 3x. And that also will be evaluated from 0 to 1.5. Okay? Now, of course, we will get into other functions that have, or that require a bit more from us as far as trying to integrate them. But that'll bring us to section 5.5 when we look at that. Right now, these formulas, or these functions are not terrible. They're not too bad. Either you'll use maybe an antiderivative formula for a trig function, or just the power rule for antiderivatives, something like that. Okay, but we will get into some that are a little bit more involved in the next section. So right now we just applied the power rule where we had to add 1 to the exponent and put that new exponent on the denominator, creating a fraction. So it ended up being 2x squared over 2, but that 2 over 2 just cancels out, so it's just x squared minus 3x. We're going to evaluate that from 0 to 1.5. And then again, x squared minus 3x, evaluating that I'm sorry, not from 0 to 1.5 again, from 1.5 to 3. We split it up. So 0 to 1.5 and then 1.5 to 3. How about that? All right. So from 1.5 to 3. So plugging in 1.5, so 1.5 squared minus 3 times 1.5. Then 0, it's going to be 0. All right, so that's this first one, evaluated at 1.5 and 0. Then we're going to say plus this one. And I use big brackets. Yeah, I know I don't lose anything. 3, so I have 3 squared minus 3 times 3 minus 1.5 squared minus 3 times 1.5. Okay? So plugging all that in, what we've got here, I'm going to plug this in, 1.5, get out of that, 1.5 squared minus 3 times 1.5 gives us a negative 2.25 right here, because minus 0, that's just going to fall off. And then plus over here, we got 9 minus 9 basically, and then minus, so this is 0, and then minus 1.5, so let me put 0 minus 1.5 squared minus 3 times 1.5. We get a negative 2.25. Okay, let's see what we've got here. So that becomes just plus there. Hold on, it shouldn't be. That one, something's wrong. Let me check my numbers. Okay, let's see. 1.5 squared minus 3 times 1.5. That gives me a negative 2.25, yeah? And then I'm saying plus okay, I'm checking my math. Something's not working out right. Okay, so we got 3 squared minus 3 times 3. And then we got 1.5 squared minus 3 times 1.5. Okay, so this should be right there. Let me try this one more time. 1.5 squared minus 3 times 1.5. Give me negative 2.25, yep. So 0 minus a negative becomes plus. So over here, this is negative. They're not supposed to cancel out. My area is not 0, so my signs are off somewhere. And I'm trying to see what I did that's throwing off my signs. 3.5, so 0 to 1.5, and then 1.5 to 3. Got that, okay. Then we've got okay, I think I see what I did wrong. 3 minus Oh, yes, I do. Oh, okay. Go back to the graph. So here's the thing. Okay. This part of the function, okay, so we've got this absolute value part around the original function, okay? This part of the function, which is supposed to be just this left part from 0 to 3/2, is actually going down. So this should actually be 3 minus 2x. That should actually be 3 minus 2x because that's the part of the function here on this side. Now, together it is absolute value, so it becomes a positive. But when you focus on just this portion of the graph, let me get it out the light, I'm sorry. It has a negative slope. So this should actually be 3 minus 2x. And that is where I am getting a negative 2.25, and I should actually be getting a positive. So when we integrate here, this is the negative and this is the positive. Because it's fine if you leave it negative 2x plus 3 or 3 minus 2x, either way is fine. But that's what's throwing off my sign. I wanted to make sure that you understood what was happening here. So that actually is plus. That one is negative right here. But yeah, so that's actually the negative right there. And then that part doesn't matter because it's 0 anyway. So let's see what we get again when I do that part. It should be positive, actually. So let's do that again. So negative 1.5 squared plus 3 times 1.5. So yeah, that should be a positive 2.25. And so then 2.25 plus 2.25 gives us 9 halves, which is 4.5. And you're probably going to want it as a fraction. But you have to be careful when you're looking at absolute value. You are supposed to split it up. But what happened is when I split it, I have to look at the graph, and that branch had a negative slope, a negative 2x. Remember, it's mx plus b. The x part, the constant in front of the x, is your slope. This part of the graph is going down. So it should have a negative in front of the x term, a positive constant. So that should have been either negative 2x plus 3 or 3 minus 2x. Same thing, they're equivalent. Okay? Let me make sure that was clear. So that is why my signs were off and why I was ending up just in area that was canceling out as area of 0, and I knew that wasn't right. Okay, so that's why, because my signs were off there. My sign was off here. Okay? So I had to look at the graph to see that this portion with absolute value, this portion is going down, has a negative slope, and this portion is going up. You actually could have maybe found just this side and doubled it because they're symmetric, but that's okay. All right, let's see if there's something else I want to examine. See here. This really may be the rest of these. got a few that are asking you to, okay, well, here's one. So you got a few that deal with trig functions. Here's one, for example, and then I'll look at something else. At number 17. So we've got the integral from -9 to 9 for e to the theta plus sine theta. So basically, with respect to d theta. So basically, you're just looking for the antiderivative. Remember, you've got a fact sheet, a formula sheet, and then also these are in the notes, the antiderivative for e to the x, the antiderivative for sine x, are in your notes for 5.1. The reverse is fine, even if it's theta instead of x, okay? So the antiderivative for e to the theta or e to the x is its own antiderivative. So it's just e to the theta. And the antiderivative for sine is cosine. And it's negative, a negative cosine, I should say. The antiderivative for sine is a negative cosine. So we got e theta minus cosine theta, and we're evaluating that from -9 to 9. Okay? So e to the 9th minus cosine to the 9th, and then minus e to the -9th minus cosine to the -9th, or cosine of -9, not to the -9. Oh my goodness, it keeps freezing. A bit. Stop freezing. One second, I'm sorry. Keeps freezing. So, okay. Now we're back. All right. So, yeah, finishing this up. So e to the 9th is just some number. We're going to just keep that. E to the 9th, because it will be some decimal. Cosine of 9, let's see what that is. That is just some number, some decimal. Cosine, let me just show you. Cosine of -9, let's see what that is. Same thing, same exact thing. So those are probably going to cancel out, is what I suspect. Let's just see. So e to the 9th minus cosine of 9, should be an exponent, cosine of 9. Then we got minus e to the -9. And then I'm going to take this through and make that plus cosine -9. So let's see here. All right. Cosine of 9 we said was -0.91 approximately. Cosine -9, -0.91. So those are going to cancel out. And you're left with e to the 9th minus e to the -9th, which is e to the 9th minus 1 over e to the 9th. Okay? All right, let me see if there's another one that I wanted to just look at. Let's see here. this problem. This is number 20. And it's y equals negative x squared plus 10x. And it says y is equal to 0. So the directions are: find the area of the region bounded by the graphs of the equation. So we're going to find the area, and remember, area is equal to the integral, the definite integral of this function. Now what we have to do is figure out what the endpoints are going to be. So we're going to look at the graph of this function to see where we're graphing negative x squared plus 10x over. And we're told to let y equal 0. I guess we're cutting it off. This function, but we're talking about the region bounded by this graph and this graph. So at y equals 0, meaning we are just focused on the upper region above the x-axis. Y equals 0 represents the x-axis. So let's put in negative x squared plus 10x. And then here we've got just y equals 0. Let's graph. So the y equals 0 again is just binding it to just the graph above the x-axis. All right. So what we're going to do is adjust our window. It looks like we don't need to worry about anything below the x-axis, so anything negative in the y's down here we don't have to worry about. So we can actually set our scale to be from maybe y equals -1 up to maybe 20, so we can get a good picture up here. And then also with x, let's say we start about right here and focus on the positive side for x. So I'm going to adjust my window to maybe -1 for the x min, and let's say 20 for the x max. And let's do the same thing with y min, -1 and 20. Now let's look at the graph. And I probably still should have went a little farther up with x. Or sorry, with the y scale. But I can see here at the bottom, the graph starts at 0 and goes from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the graph we're talking about, the area we're talking about under this curve, is from 0 to 10. Okay? And with respect to x is how we're integrating. So from there, it's pretty standard. It's just you had to see what your interval was going to be by looking at the graph. And again, I can adjust my window. Let's make the y max 30. See if that's even a better picture. Yeah, that's better. But you can see how the graph is limited from x is 0, x equals 0 to x equals 10. So our area will equal, we're going to integrate, find the antiderivative. This will be -2 plus 1 exponent. So negative out front because it was negative already. 2 plus 1 is your exponent over 2 plus 1. And then here, 1 plus 1 over 1 plus 1. And we're evaluating from 0 to 10. So this is a negative x to the third power over 3 plus 10x squared over 2, which is a -1/3 x to the third power plus 5x squared. Then we'll evaluate that from 0 to 10. Okay? That's it. Plug in 10, -1/3, 10 cubed, plus 5 times 10 squared, minus -1/3. Oh, this one's at 0. You don't even have to do this one. That's just going to go away to 0. So this ends up being a -1,000 over 3. So 10 cubed is 1,000. And then this is 5 times 100, which is just 500. So -1,000 over 3 plus 500 equals, cleaning that up, simplifying that, equals 500 over 3. Okay? So that is all I have for this section. Excuse me. Again, now, since you know that you're just equating antiderivatives with area under the curve, you can actually go back and look at some more problems in 5.3. And instead of applying limits, you can actually just apply this rule. You find the antiderivative and then evaluate it from over the endpoints. Okay? But that's all I have today, and I will see you guys soon.